Hi friends, now let's get into an algorithm that checks whether the situation gets into deadlock or not before allocating any resource to any process. So that is what we call a banker's algorithm. So this is developed by Digistra. It simulates a bank giving loans to customers with a credit limit. So there is a bank which has got a customers, and these customers have their credit limits depending on their capacity to repay the loan and all that. And depending on the credit limit, the customers are allowed to take the loans. But there are many customers, and each one having a different credit limit, and the bank has got limited funds. So in the situation like this, the whole process has to be managed most efficiently so that the bank will be always in profit. Almost every customer who wants a loan and has proper credibilities, has a requirements less than the credit limits should be satisfied. No customer should be said no for reasons of not having fund or for any other such reasons. It can be only the customer out of the credit limit only can be rejected, but not on the normal grounds. So that's a algorithm developed by Digistra, used for a banking system, and hence the name banker's algorithm. This algorithm is used by the bankers to decide whether a loan application to be sanctioned or not. So the data structures used with this banker's algorithm, the one is one-dimensional vector which is called available. This talks of number of instances of each resource type currently available. So we have many resources, and each resource may have multiple instances. So for each resource, how many instances are currently available for usage? That's available. Next is the maximum, that is a maximum demand for each process. So each process says that I want these number of instances of this particular resource, these number of instances for the other type of resource, and so on. So the max is the demand of each process. That means for every process there will be one vector stating what is the maximum requirement of the instances of each resource it wants. So it's a 2D matrix, and then we have an allocation matrix, that again each row talks about one process and each column talks about one resource type. And currently each process, how many resource types of each how many instances of each resource type are allocated is given by this matrix allocation. Then the difference between what is required and what is allocated is the need. How much more is required? Actually, maximum was the total requirement, and as of now allocation is available to us, and this need is still required. So when a process requests for resources, so first thing is to check if the request is less than the need or not. So what is needed? So we know totally how much is required, maximum requirement we know, how much is allocated to them is known, so the difference of them is what is the need is. And now we are requesting, a process sends a request, and that request has to be less than the need. It can't ask more than what it requires. Therefore, first thing is make sure that the request is less than the need, and second thing is make sure that the request is less than or equal to what is available. You can't accept any request which is greater than what is available. Therefore, ensure that the request is less than or equal to the need, and the request is less than or equal to available. That means the process is not authorized to request more than what it wanted, and request should be such that it can be fulfilled. That means the available resources are more than what is requested. At least what is requested, that much is available. If so, then the next option, then temporarily allocate and update the matrices. So if a process is requesting, then if these two conditions are true, then assume that it is allocated and the matrices are updated properly, and then check the safety check algorithm. So can the system find a sequence where every process finishes? So can we have a sequence of processes executed one after other, so that each one can complete their task? If so, then we can say it is safe, otherwise unsafe. If it is safe, then grant the request. So we had a request from the process, we just assume that we are allocating it, and if we make the safety check, and if the safety test is okay, then we grant the request. If it is not safe, just deny the request and restore the previous state. Whatever we have done changes here, restore the previous state, and just ask that process to be in the waiting state. Keep waiting till the resources are available. Okay, let's take an example. Without example we cannot understand anything. So let us assume that we have three resources, A, B and C, and the number of instances of A, B, C are A 10 instances, B 5 instances, C 7 instances respectively. So let's assume that there are 5 processes, P0 through P4, and at this instant these processes are already allocated some resources in the past. So at this instant, if I look at it, what each process is having. So process P0 is having nothing of A but 1 instance of B, nothing of C. Process P1 having 2 instances of A, none of B and C. Process P2 has got 3 instances of A, none of B, 2 instances of C. P3 2, 1, 1 respectively, and P4 not, not and 2 respectively for A, B and C. And before starting, the processes have said that they would require maximum number of instances. Like P0 wanted maximum 7, so it is not going to ask more than 7 any time. So it would require maximum 7 of A, maximum 5 of B, maximum 3 of C, and so on. So that matrix talks about each process requesting what maximum they require. So this is the maximum requirement, and this is at this instant what all allocated. Now at this instant, if I know, then what else is missing. So we wanted 7 maximum, nothing is allocated, therefore in future we require 7. So we wanted 5 of B for P0, 1 is allocated, so 4 more required. So maximum minus current allocation will be the need. Just subtract this matrix from this matrix to get this matrix. Done. So these are already allocated. This is maximum. This matrix talks of the need, and we have 10 instances of A, 5 instances of B, and 7 instances of C. So currently how many are already allocated? So if you look at A, 2 plus 3 5, 5 plus 2 7, 7 are already allocated, 10 were available, 7 are already allocated, therefore 3 are still waiting for their allocation. So 3 resources of A are available for allocation. Same way if you look for B, this is 1 plus 1 2, 2 are already allocated, total were 5, so 5 minus 2, 3 more are available for B. And for C, 2 plus 1 plus 2 5 are allocated, we had 7, so 7 minus 5, 2 are still remaining. Done. So that's the basic thing where we begin our task. The problem given was the total instances of the various resources, current allocation, maximum need. These 3 data were given to us. From these 3 data we calculated the need matrix, and from this and this we have calculated available. So let's begin to see, can we fulfill any of these needs, and if so, then in what sequence I can fulfill them, and if I start fulfilling one by one process, then will there be any sequence of processes so that each of these 5 processes get their chance to complete their task? If so, let's check it. So this is the allocated matrix, and this is the required matrix, need matrix. So we have allocated this, and we have this more requirement, and currently we have 3 3 2 resources available, 3 of A, 3 of B, 2 of C are available. So what is required for P0? 7 4 3. So 7 of A required. So can we allocate? Definitely no. What about P1? 1 2 2 required, and we have 3 3 2. So 3 is available, 1 required, okay. 3 available, 2 required, okay. 2 available, 2 required, okay. Therefore P1 can be given a chance to work. So let us allocate these 1 2 2 resources from the available list to process P1 and start P1 working. So once P1 is done, then P1 is completed, then it was holding 2 resources, and once P1 is complete its job, these 2 resources of A or instances of A are released, so 2 gets added to available. So 3 instances of A were there, now it has become 5. Now 5 3 2 instances are available for A, B, C respectively. Now what is next? So 7 4 3 no, 6 0 0 no, because we have only 5. P2 requires 6, not possible. What about P3? 0 1 1, yes, of course we can satisfy. We have 5, we don't want any of A. We have 3, we want 1 of B. We have 2, we want 1 of C. So can be done. Therefore allocate these resources 1 1 of B and C to process P3, and P3 work will be done. So P3 completes its job. Once P3 completes its job, these 2 1 1 gets released. So A will be added with 2, B will be added with 1, C will be added with 1. So therefore 5 plus 2 7, 3 plus 1 4, 2 plus 1 3, that is 2 1 1 get added here. So we get 7 4 3. So that is 7 instances of A, 4 instances of B, 3 instances of C. Now we can look for the first line again. So P0 can be taken up. So 743 required, 743 available. So 743 required, 743 available. Therefore P0 can be taken up, and if P0 is done, then this one instance of B will be released, and because of that, with this 743 will now become 753. And this 753, what is that? P1 is over, P3 is over, P0 is over. Then P2, if you look at it, we can think of next P2, but I have taken P4 here. So P4 can be taken up because it requires 431, we have 753, so P4 is taken up. If P4 is taken, then 2 instances of C gets released after that, and this 2 gets added to C, so it becomes 5. Now I can take P2, so the requirement is 611, so 600, so we have 7 here, so P2 can be comfortably solved. Therefore, what we have seen here is there is a sequence P1, P3, P0, P4, P2. In this, if we run, then P0, P1, P2, P3, P4, all 5 processes will run, and there is no chance of any process getting waited forever, so no chance of deadlock. Therefore, whatever was requested can be allocated. So we can say that whatever is requested can be allocated, so that there is no issue, no problem of getting into deadlock, and hence it is a safe state, so we can allocate that. The same we can look into another way. So we start with again P1, because P0 cannot be taken up. P1 we take up first, then we go for P3, then we go for P4 instead of P2. Now instead of P0 we can go for P4, then we can go for P0, then finally we can go to P2. So there is another sequence P1, P3, P4, P0, P2. That way also we can take it up. And after P4 we can take up P2 also, because P2 requirement is 600, and after P4 we have 743, or even after P3 also we can take up P2, because we have 7 here, so we can take up P2 here. So there are many ways this problem can be solved. So there are many sequences in which this problem can be solved, and hence we find that this is a safe state, and therefore the resources request can be allocated. We can say yes to the request from the processes. So this whatever requests are there, so the total requirements fulfill the banker's algorithm, and say that at the end of the banker's algorithm we find that we are still in the safe state, and hence this process can continue and there is no risk of deadlock. So this way we can just identify that we just imagine that if resource is allocated, what would happen. So we find a series of actions, so a sequence of processes running one after other, and if we get at least one sequence that lead to running of all the processes, then yes, we are done with, and the banker's algorithm declares success, and whatever the request was there will be allocated, and the situation is safe and is not going to enter into deadlock, and hence we can honor that request and allocate the resources to that process. So that's banker's algorithm. To understand more details, more depth, let's take up some more examples in the coming session. Thank you.